It is impossible for any species to cross the Milky Way galaxy. So where is everybody in the universe? That's a question that has been present in both science and philosophy for decades. In fact, the more we explore the universe, the more perplexing this question becomes. And yet, it's incredibly simple. Enrico Fermi posed this question in 1950, and since then it has become what we call the Fermi paradox. Our galaxy is incredibly ancient, about 13 billion years old. It contains about 400 billion stars. And thanks to the discovery of exoplanets, we now understand that planets are not rare oddities but the norm. Most stars have planetary systems. The raw materials for life are everywhere: carbon, oxygen, nitrogen, hydrogen. These elements are formed in the cores of stars and then dispersed throughout the galaxy through stellar explosions, enriching planets everywhere with the same chemical foundation. With this in mind, vast civilizations may have emerged billions of years before we did. They had billions of years to expand, explore, and build enormous technological civilizations, leaving traces so clear that any intelligent observer would recognize them immediately. Yet when we look outside, we find nothing. No colossal structures, no continuous radio signals, no evidence of large-scale space technology, no visiting spacecraft, only silence. A complete and utter cosmic silence. Over the years, many explanations have been proposed to resolve the Fermi paradox. Perhaps life itself is incredibly rare. Perhaps intelligence almost never arises. Perhaps technological civilizations tend to destroy themselves soon after they appear. Perhaps extraterrestrial civilizations are deliberately hiding. Perhaps they are already present, but in forms we fail to recognize. But I want to make the case for what I believe is the most fundamental explanation of all. An explanation that does not rely on guessing alien motivations or speculating about their technology or assuming pessimistic outcomes for civilizations. The explanation is simply this: crossing the galaxy is impossible, not merely difficult, not just extraordinarily challenging, but fundamentally impossible for any biological species, no matter how advanced, how determined, or how long-lived. The galaxy is not something that can be crossed, colonized, or fully explored by beings like us, or by any other organisms that evolve on planets elsewhere. The distances involved are simply too vast. The timescales are too extreme. The energy demands are overwhelming, and the environment of interstellar space is relentlessly hostile to life. The Milky Way is, in effect, a desert, a vast, empty, unforgiving expanse, dotted with rare islands of habitability that are permanently separated, forever unreachable from one another. And when we understand why this is so, when we grasp the true barriers to galactic expansion, we learn something deeply important about our position in the universe and about the nature of life and intelligence itself. So let us begin with the most obvious obstacle, the one that underpins everything else. Distance. The Milky Way galaxy measures roughly 100,000 light-years across. That is the distance light travels in 100,000 years, moving at 300,000 kilometers per second, the maximum speed allowed by the laws of physics. Even traveling at the speed of light, crossing the galaxy would require 100,000 years, and nothing that possesses mass can ever reach that speed. As objects with mass are accelerated closer and closer to light speed, they demand increasing amounts of energy. As the speed approaches light speed, the energy required approaches infinity. This is not a technological limitation. It is a fundamental consequence of special relativity, a rule of the universe that cannot be bypassed with clever engineering or superior machinery. Any realistic form of interstellar travel must therefore occur at speeds far below light speed, perhaps at 1% or 10% of light speed. Even if we adopt an extraordinarily optimistic view of propulsion technology and imagine spacecraft traveling at 10% of light speed, a capability far beyond anything we can currently conceive, crossing the galaxy would still take around 1 million years. At 1% of light speed, which is still wildly optimistic, the journey would last 10 million years. These are not timescales that make sense for human beings. They are not even timescales that make sense for civilizations. These are geological timescales. periods over which species evolve and disappear, over which planetary climates transform completely, over which stars are born and die. To understand what this means, consider that 10 million years ago, humans did not exist. Our hominid ancestors were only just beginning to diverge from other apes. Everything we call human civilization, writing, agriculture, cities, culture, science, has emerged within the last 5,000 years. That is just 0.05% of 10 million years. The entire existence of our species, Homo sapiens, spans perhaps 300,000 years, which is only 3% of 10 million years. So when we speak realistically about crossing the galaxy, we are describing journeys that last thousands of times longer than the lifetime of our species, and millions of times longer than all of recorded human history. These are timescales that render the entire endeavor essentially meaningless when viewed from the standpoint of any species or any civilization. You might reasonably object and ask about generation ships. What about populations that live aboard spacecraft for many generations, with descendants eventually reaching destinations their ancestors once set out for? Generation ships are often proposed as a solution to the problem of time. If a single lifetime is not enough to complete the journey, then spread that journey across many lifetimes. The idea is to create self-sustaining populations on spacecraft that endure across generations, with each generation born on the vessel, living their entire lives there, reproducing, aging, dying, until at last their distant descendants arrive at the intended destination. This idea is a familiar theme in science fiction, and in principle, it does not violate the laws of physics. But I want to argue that while it may be physically possible in theory, it is practically impossible for biological organisms. The challenges involved in maintaining viable populations on spacecraft for thousands or even millions of years are overwhelming for any evolved life form. Let me explain why. The first issue is one of scale and resources. A generation ship must be completely self-sufficient for the entire duration of its journey, which could span thousands or millions of years. That requires a closed-loop life support system capable of recycling everything with almost perfect efficiency. It demands agricultural systems that can produce all necessary food indefinitely. It requires manufacturing capabilities to repair and replace every component that will inevitably fail. It also demands sufficient genetic diversity to maintain healthy populations across thousands of generations, along with social and governance systems that can remain functional despite unavoidable conflicts and pressures. The size and mass of such a spacecraft would be vast. You would need agricultural areas, likely hundreds of square meters per person, to achieve complete food self-sufficiency. You would need living quarters, manufacturing facilities, storage for spare parts and raw materials, shielding against cosmic radiation, power generation systems, propulsion systems, and a population numbering in the thousands to preserve genetic diversity. Altogether, you are looking at a spacecraft with a mass of millions of tons, possibly tens or even hundreds of millions of tons, and every single kilogram of that mass must be accelerated to interstellar speeds and then slowed down again upon arrival. The energy demands are extraordinary. At 1% of the speed of light, the kinetic energy of a spacecraft with a mass of 1 million tons is roughly 4.5 times 10 to the power of 22 joules. That is comparable to the energy output of our sun over several hours, or the total energy contained in thousands of nuclear weapons just to accelerate the ship. You would need roughly the same amount of energy again to decelerate it. So where does that energy come from? Our current propulsion technologies, chemical rockets and ion drives, are utterly inadequate. You would require fusion rockets, antimatter propulsion, or laser sails driven by enormous ground-based lasers. All of these remain theoretical. None have been demonstrated at anything close to the scale required for interstellar travel, and each faces formidable technical challenges that may never be overcome. But let us imagine that somehow the energy problem is solved. You build the immense spacecraft and accelerate it to interstellar velocity. Now you confront an even more daunting problem: maintaining that spacecraft for thousands or millions of years. Every system will eventually fail. Electronics degrade under constant exposure to cosmic radiation. Mechanical components wear down. Biological systems change. Agricultural crops evolve. The human microbiome shifts. Decomposer organisms adapt in ways that could destabilize carefully balanced ecosystems. The ship becomes a tiny, closed world that must remain stable and functional for time spans far longer than any technological system has ever endured. Far longer, in fact, than any human society has remained continuous and coherent. We have no examples of technological systems operating reliably for even thousands of years, let alone millions. The pyramids have endured for thousands of years, but they are passive stone structures. Active systems, machines, electronics, anything requiring maintenance, fail on much shorter timescales. Even with constant maintenance and repair, technological systems do not last forever. Eventually, spare parts are exhausted, critical knowledge is lost, or materials degrade beyond recovery, and a generation ship cannot be resupplied. Everything it will ever need must be carried at the outset, or manufactured from materials brought along using equipment that is also carried. If essential systems such as life support, agriculture, or power generation fail and cannot be repaired with the available resources and knowledge, then everyone aboard dies. The ship becomes nothing more than a tomb drifting silently through interstellar space. Then there is the biological challenge of sustaining viable populations across thousands of generations. Small populations are susceptible to inbreeding, genetic drift, and the accumulation of harmful mutations. Maintaining genetic health would require populations numbering in the thousands, along with careful management of reproduction to prevent inbreeding and preserve diversity. But managing reproduction means controlling who has children with whom and how many children are born. That implies an extraordinary level of social control over one of the most intimate aspects of human life. And this control would have to be maintained successfully for thousands of generations, which seems sociologically implausible. Beyond that, populations living in isolated environments inevitably evolve. That is not speculation, it is a fundamental principle of biology. Mutations would steadily build up, natural selection would continue to act, genetic drift would quietly reshape gene pools, and populations would change as the generations pass. After thousands of generations, living in the utterly distinctive environment of a spacecraft, with artificial gravity produced by rotation, constant exposure to cosmic radiation despite shielding, artificial light, recycled air, and a severely limited genetic pool, that population would almost certainly diverge genetically from humans on Earth. Over time, they would acquire genetic traits tuned specifically to life aboard the ship. At the same time, harmful mutations could accumulate as a consequence of small population size and persistent radiation exposure. By the time they reach their destination, assuming they ever did, they might constitute a distinct subspecies or even a separate species altogether, potentially less capable of surviving on planetary surfaces than the humans from whom they descended. Now, let me turn to the psychological and social dimensions of generation ships, because these challenges may be even more overwhelming than the technical or biological ones. Imagine being born on a generation ship. This was never your choice. The decision was made by your ancestors many generations before you existed. You spend your entire life inside a sealed, artificial habitat, perhaps only a few square kilometers of living space, shared with thousands of other people. You will never see Earth. You will never walk beneath a natural sky, never experience a planetary environment, never know what it means to leave the ship or explore beyond its rigid boundaries. Your entire life is devoted to a mission you did not choose, aimed at an outcome you will never witness. The destination lies thousands of years in the future, far beyond your lifespan. Your children will not reach it, nor will your grandchildren. Dozens, perhaps hundreds of generations will be born, live, and die aboard this vessel before arrival. So, what sustains you? What gives your life meaning when you are merely one link in an immense chain? When your primary purpose is simply to survive long enough to reproduce so that the journey continues, how do you preserve morale, maintain social cohesion, and sustain commitment to the mission across so many generations? History gives us little confidence. It suggests this would be extraordinarily hard. Human societies undergo profound change over far shorter timescales. Languages shift and split, cultures evolve, political systems emerge and collapse, religious beliefs transform, and values and priorities drift over thousands of years. On a generation ship, you would expect immense cultural evolution. There is no guarantee that distant descendants would feel any obligation to the original mission. At some point, a generation might decide the journey is meaningless, that the ship should turn back, alter course, or abandon the destination entirely and simply exist aboard the vessel indefinitely. Another generation might face social collapse, civil conflict, epidemic disease, or widespread psychological breakdown that brings the mission to an end. Critical knowledge and skills required to operate and repair the ship could be lost if education systems fail, or if people simply lose interest in maintaining technical expertise. The likelihood of uninterrupted success across thousands of generations is vanishingly small. Far more likely is failure long before arrival. Technical breakdowns, biological degradation, or social collapse would eventually doom the endeavor. And even if a tiny fraction of generation ships succeeded, even if 1 in 1,000 or 1 in a million reached their destinations, that would still be insufficient to populate a galaxy. Galactic colonization would require millions of successful missions, implying billions of attempts, something utterly implausible for any civilization. So generation ships do not solve the problem of time. They are either impossible in practice or so implausibly difficult that they cannot form a viable route to galactic expansion. You might then suggest alternatives. What about suspended animation or cryogenic freezing, where crew members sleep through the journey and awaken at the destination? This would address the psychological and social issues of generation ships and greatly reduce life support demands during transit. But suspended animation presents its own seemingly insurmountable obstacles. We do not know how to freeze and revive humans safely. We do not know how to prevent catastrophic cellular damage caused by ice crystal formation during freezing. We do not know how to preserve frozen bodies for thousands of years without gradual degradation. We also do not know how to power and maintain cryogenic systems reliably for such immense spans of time. And even if all of these problems were solved, the spacecraft would still require autonomous systems capable of navigation, hazard avoidance, and self-repair throughout the journey. That demands artificial intelligence far beyond anything we currently possess. It would require intelligence able to function independently for thousands or even millions of years without human supervision, making complex decisions and repairing itself. Such an intelligence might reasonably be regarded as a separate form of being from the frozen humans it supports, raising the question of whether this represents biological colonization at all, or instead machine colonization. What, then, about transferring consciousness into computers, sending digital minds rather than physical bodies? This would bypass biological constraints entirely. Computers do not require food, air, or gravity. In principle, they could operate for extraordinarily long periods and could be duplicated for redundancy. Yet, uploading consciousness presents deep philosophical and technical uncertainties. We do not know whether consciousness can exist independently of biological brains. We do not know whether digital brain simulations would truly be conscious or merely exquisitely detailed imitations. We do not know whether uploaded minds could remain psychologically stable over journeys lasting thousands or millions of years. And even if uploading were possible, the resulting entities would differ so profoundly from biological organisms that it becomes unclear whether the original species is colonizing the galaxy or whether an entirely new form of intelligence has emerged. Every proposed solution to the time problem either fails technologically, fails biologically, fails psychologically and socially, or alters the colonizers so radically that they cease to be the species that began the journey. Time itself stands as a fundamental barrier that biological organisms cannot overcome when attempting to cross the galaxy. But let me go on, because time is not the only obstacle, and perhaps not even the deepest one. Let me talk about destinations, about where you might choose to go if the problem of time could somehow be overcome. Because when you examine this carefully, you begin to see that there is nowhere truly worth going, that our galaxy does not actually offer destinations that would justify the immense costs and difficulties of interstellar travel. When we imagine colonizing the galaxy, we tend to picture Earth like planets, worlds where humans could live, flourish, and build civilizations. But planets that are genuinely Earth-like, places where you could breathe the air, drink the water, and grow Earth crops without extensive alteration, are extraordinarily rare and may not exist at all within any reasonable distance. It is worth explaining what Earth-like really means, because the requirements are far more demanding than most people realize. You need a planet of the correct size, large enough to hold on to an atmosphere through gravity, yet small enough that the surface gravity remains tolerable for humans or other evolved life. It must orbit within the habitable zone of its star, close enough for liquid water to exist, but far enough away to avoid a runaway greenhouse effect. You also need the right kind of star, one that is stable, long-lived, and not prone to violent flares that would bathe the planet in lethal radiation. The planet must have an atmosphere with the right composition, oxygen but not too much, nitrogen, trace gases, and minimal toxins. The atmospheric pressure must be just right. Too low and you cannot breathe. Too high and you are crushed. Liquid water must be readily accessible on the surface. A magnetic field is required to shield the surface from cosmic radiation. Geological activity is needed to recycle nutrients and regulate climate over geological timescales. A large moon helps stabilize the planet's axial tilt, preventing extreme and chaotic climate variations. And crucially, the planet must be free from incompatible biochemistry. There must be no native bacteria or viruses capable of infecting colonists, no indigenous plants or animals that are toxic or hostile, no biochemical incompatibilities that would prevent Earth organisms from surviving and thriving. When you add all of these requirements together, when you consider how many conditions must align perfectly, it becomes clear that truly Earth-like planets are vanishingly rare. We have now discovered thousands of exoplanets, and while some lie within habitable zones, and some are roughly Earth-sized, none satisfy all the criteria required for genuine Earth-like habitability. From what we can determine with current observations, most of the exoplanets we have found are gas giants, super-Earths with crushing gravity, tidally locked worlds with permanent day and night sides, or planets orbiting flare stars that would sterilize their surfaces with intense radiation. At this point, you might argue that we do not need planets that are exactly like Earth. You might say that humans could adapt, that technology could be used to create habitable environments, even on worlds that are not naturally suited to us. This is the idea behind terraforming, the deliberate modification of planets to make them compatible with Earth life. But I have discussed terraforming before, and I have explained why I believe it is essentially impossible. The energy, resources, and timescales required to alter an entire planetary environment are far beyond what any civilization could realistically achieve. And more fundamentally, if you are relying on technology to create your environment, if you are living inside artificial habitats with manufactured atmospheres, radiation shielding, and synthetic food systems, then there is no real advantage to being on a planet at all. You could do exactly the same thing in space habitats, on asteroids, or in orbit around gas giants. If you cannot use the planet's native environment, then the planet itself offers no meaningful benefit. This is why the destination problem is so severe. There is nowhere to go that would naturally support biological colonists without vast technological support. And if vast technological support is required regardless, then why travel for thousands or millions of years to distant star systems when you could build habitats within your own system with far less effort and expense? The lack of suitable destinations fundamentally undermines the case for galactic colonization by biological species. But there is another barrier, perhaps the most fundamental of all, and that is energy. Everything I have described, accelerating enormous spacecraft to interstellar speeds, sustaining them for thousands or millions of years, terraforming planets, or constructing artificial habitats, demands staggering amounts of energy. And energy is constrained by the laws of physics in ways that no amount of technological ingenuity can escape. A civilization's energy budget is ultimately limited by what it can extract from its star and its surrounding environment. Humanity today uses roughly 6 times 10 to the power of 20 joules of energy per year, which is about 0.001% of the energy Earth receives from the Sunday. If we were able to capture all of the solar energy that reaches Earth, around 1.7 times 10 to the power of 17 watts, we would have roughly 100,000 times more energy than we currently consume. That may sound enormous, but consider this. Accelerating a spacecraft with a mass of 1 million tons to just 1% of the speed of light requires about 4.5 times 10 to the power of 22 joules of energy. That is roughly 700 times more energy than all the sunlight that strikes Earth in an entire year. So even if we captured every bit of solar energy reaching our planet, we could launch only one modest-sized interstellar ship every 700 years. And that calculation accounts only for acceleration. You would need a comparable amount of energy for deceleration at the destination. One might then imagine constructing a Dyson sphere, a hypothetical megastructure designed to capture most or all of a star's energy output. Our Sun produces about 3.8 times 10 to the power of 26 watts. With access to that level of energy, interstellar missions could, in principle, be launched far more frequently. But building a Dyson sphere would itself demand extraordinary amounts of energy, resources, and time. You would need to dismantle planets to obtain sufficient material. You would have to manufacture and precisely position vast numbers of orbital collectors. You would need to maintain the structure against gravitational and dynamical instabilities. This is engineering on a scale that may exceed the capabilities or the patience of any biological civilization. And even with a Dyson sphere, even with the full energy output of a star at your disposal, galactic colonization would remain prohibitively expensive. Sending ships to thousands or millions of stars, supporting them during journeys lasting thousands or millions of years, and then terraforming worlds or constructing habitats at their destinations would consume significant fractions of a civilization's total energy budget for immense spans of time. At that point, one has to ask whether this is a rational use of resources. What is the return on such an investment? What do you actually gain from galactic colonization that could justify expenditures on this scale? I cannot think of any plausible answer. Let me talk about destinations, about where you might choose to go if the problem of time could somehow be overcome. Because when you examine this carefully, you begin to see that there is nowhere truly worth going, that our galaxy does not actually offer destinations that would justify the immense costs and difficulties of interstellar travel. When we imagine colonizing the galaxy, we tend to picture Earth like planets, worlds where humans could live, flourish, and build civilizations. But planets that are genuinely Earth-like, places where you could breathe the air, drink the water, and grow Earth crops without extensive alteration, are extraordinarily rare and may not exist at all within any reasonable distance. It is worth explaining what Earth-like really means, because the requirements are far more demanding than most people realize. You need a planet of the correct size, large enough to hold on to an atmosphere through gravity, yet small enough that the surface gravity remains tolerable for humans or other evolved life. It must orbit within the habitable zone of its star, close enough for liquid water to exist, but far enough away to avoid a runaway greenhouse effect. You also need the right kind of star, one that is stable, long-lived, and not prone to violent flares that would bathe the planet in lethal radiation. The planet must have an atmosphere with the right composition, oxygen, but not too much, nitrogen, trace gases, and minimal toxins. The atmospheric pressure must be just right, too low and you cannot breathe, too high and you are crushed. Liquid water must be readily accessible on the surface. A magnetic field is required to shield the surface from cosmic radiation. Geological activity is needed to recycle nutrients and regulate climate over geological timescales. A large moon helps stabilize the planet's axial tilt, preventing extreme and chaotic climate variations. And crucially, the planet must be free from incompatible biochemistry. There must be no native bacteria or viruses capable of infecting colonists, no indigenous plants or animals that are toxic or hostile, no biochemical incompatibilities that would prevent Earth organisms from surviving and thriving. When you add all of these requirements together, when you consider how many conditions must align perfectly, it becomes clear that truly Earth-like planets are vanishingly rare. We have now discovered thousands of exoplanets, and while some lie within habitable zones and some are roughly Earth-sized, none satisfy all the criteria required for genuine Earth-like habitability. From what we can determine with current observations, most of the exoplanets we have found are gas giants, super-Earths with crushing gravity, tidally locked worlds with permanent day and night sides, or planets orbiting flare stars that would sterilize their surfaces with intense radiation. At this point, you might argue that we do not need planets that are exactly like Earth. You might say that humans could adapt, that technology could be used to create habitable environments even on worlds that are not naturally suited to us. This is the idea behind terraforming, the deliberate modification of planets to make them compatible with Earth life. But I have discussed terraforming before, and I have explained why I believe it is essentially impossible. The energy, resources, and timescales required to alter an entire planetary environment are far beyond what any civilization could realistically achieve. And more fundamentally, if you are relying on technology to create your environment, if you are living inside artificial habitats with manufactured atmospheres, radiation shielding, and synthetic food systems, then there is no real advantage to being on a planet at all. You could do exactly the same thing in space habitats, on asteroids, or in orbit around gas giants. If you cannot use the planet's native environment, then the planet itself offers no meaningful benefit. This is why the destination problem is so severe. There is nowhere to go that would naturally support biological colonists without vast technological support. And if vast technological support is required regardless, then why travel for thousands or millions of years to distant star systems when you could build habitats within your own system with far less effort and expense? The lack of suitable destinations fundamentally undermines the case for galactic colonization by biological species. But there is another barrier, perhaps the most fundamental of all, and that is energy. Everything I have described, accelerating enormous spacecraft to interstellar speeds, sustaining them for thousands or millions of years, terraforming planets, or constructing artificial habitats, demands staggering amounts of energy. And energy is constrained by the laws of physics in ways that no amount of technological ingenuity can escape. A civilization's energy budget is ultimately limited by what it can extract from its star and its surrounding environment. Humanity today uses roughly 6 times 10 to the power of 20 joules of energy per year, which is about 0.001% of the energy Earth receives from the Sunday. If we were able to capture all of the solar energy that reaches Earth, around 1.7 times 10 to the power of 17 watts, we would have roughly 100,000 times more energy than we currently consume. That may sound enormous, but consider this. Accelerating a spacecraft with a mass of 1 million tons to just 1% of the speed of light requires about 4.5 times 10 to the power of 22 joules of energy. That is roughly 700 times more energy than all the sunlight that strikes Earth in an entire year. So even if we captured every bit of solar energy reaching our planet, we could launch only one modest-sized interstellar ship every 700 years. And that calculation accounts only for acceleration. You would need a comparable amount of energy for deceleration at the destination. One might then imagine constructing a Dyson sphere, a hypothetical megastructure designed to capture most or all of a star's energy output. Our Sun produces about 3.8 times 10 to the power of 26 watts. With access to that level of energy, interstellar missions could, in principle, be launched far more frequently. But building a Dyson sphere would itself demand extraordinary amounts of energy, resources, and time. You would need to dismantle planets to obtain sufficient material. You would have to manufacture and precisely position vast numbers of orbital collectors. You would need to maintain the structure against gravitational and dynamical instabilities. This is engineering on a scale that may exceed the capabilities or the patience of any biological civilization. And even with a Dyson sphere, Even with the full energy output of a star at your disposal, galactic colonization would remain prohibitively expensive. Sending ships to thousands or millions of stars, supporting them during journeys lasting thousands or millions of years, and then terraforming worlds or constructing habitats at their destinations would consume significant fractions of a civilization's total energy budget for immense spans of time. At that point, one has to ask whether this is a rational use of resources. What is the return on such an investment? What do you actually gain from galactic colonization that could justify expenditures on this scale? I cannot think of any plausible answer. There is a common assumption that any intelligent species will feel an almost irresistible urge to explore, to look outward and discover what exists beyond its home, to place itself within a wider cosmic setting. Curiosity is, without doubt, a real and powerful force. As a species, we have ventured into every environment on our planet, from deep oceans to frozen poles, often at immense cost and significant risk. But exploration, crucially, does not require colonization. Exploration can be achieved through robotic probes, through telescopes, through remote observation carried out entirely from within one's own stellar system. These approaches are vastly cheaper, far more efficient, and dramatically more practical than sending biological organisms on journeys lasting thousands of years. If the aim is to understand other star systems, to study exoplanets, to map the range of environments that exist across the galaxy, then machines accomplish this task far more effectively than crewed, life-bearing expeditions. So curiosity may drive the construction of powerful telescopes and the launch of probes, but it does not naturally lead to biological colonization. And even exploration itself has natural limits. How many stars must you examine before you have learned what you set out to learn? After studying dozens or hundreds of nearby systems, after characterizing thousands of planets using instruments and probes, what new insight is gained by visiting the millionth star? At some stage, the returns begin to diminish. The fundamental patterns have been revealed. The broad diversity of planetary systems becomes clear. Each additional mission delivers progressively less genuinely new information. For this reason, curiosity may justify a phase of exploration, but it does not support the idea of galaxy-spanning colonization programs lasting millions of years and involving billions of separate missions. There may be other motivations I have not fully considered. Perhaps cultural or religious imperatives to spread across the cosmos, or competition with other species for territory, or some deep biological drive that I am failing to appreciate. Yet when I examine these possibilities, they appear weak when measured against the immense costs and extraordinary timescales involved. Cultural and religious motivations evolve and transform over centuries or millennia. How could they remain coherent enough to sustain projects lasting millions of years? Competition with other species makes little sense when the galaxy is so vast that encounters would be vanishingly unlikely, and when competition for resources across interstellar distances has no meaningful economic logic. As discussed earlier, biological drives to expand and reproduce operate on evolutionary timescales of thousands or millions of years, but only in environments where expansion offers a direct reproductive advantage. These drives evolved for life on planets. It is far from clear that they translate to expansion across the galaxy, where no individual reproductive benefit exists. The more I reflect on motivation, the less convincing the case becomes that any biological species would genuinely pursue full-scale galactic colonization, even if it possessed the technology to do so. The costs are overwhelming, the timescales immense, and the benefits either vague or entirely absent. It seems far more plausible that species remain within their home systems, perhaps exploring nearby space using machines, perhaps establishing limited colonies within their local region if they are particularly ambitious, but not attempting to occupy the entire galaxy. And this leads to a remarkably simple resolution of the Fermi paradox. We see no evidence of galactic civilizations because galactic civilizations do not exist. Comprehensive galactic colonization is effectively impossible for biological species, regardless of how advanced their technology becomes. Now, let me turn to an idea often proposed as a way to bypass these obstacles. the concept of self-replicating probes. These would be small robotic spacecraft that travel to other star systems, use local materials to construct copies of themselves, and send those copies onward, creating an exponentially expanding wave across the galaxy. This concept is often referred to as the von Neumann probe scenario, named after the mathematician who studied self-replicating systems. The argument is that even if biological colonization is unworkable, machine-based expansion might succeed. Machines do not require life support, they are not constrained by limited lifespans, and they do not suffer psychological effects from isolation or confinement. They can be compact and therefore cheaper to launch, and if they can replicate themselves, only one or a small number of initial probes would be required. Each probe would arrive at a new star system, build copies of itself, and those copies would continue outward, producing exponential growth that could, in principle, explore or colonize the galaxy in a relatively short period by cosmic standards. This idea is often presented as a solution to the Fermi paradox. If self-replicating probes are feasible and represent an efficient method of galactic exploration, then any technological civilization might be expected to deploy them. And if that were the case, we might expect to see evidence of their presence throughout the galaxy. The fact that we do not suggests either that such civilizations do not exist, or that self-replicating probes are impossible or fundamentally undesirable. I believe the latter explanation is the more convincing one. Self-replicating probes face profound challenges that render them impractical, if not impossible, for genuine galactic exploration. Let me explain. First, true self-replication is extraordinarily difficult. It would require a probe to identify suitable raw materials within an alien star system, extract and refine those materials, manufacture every complex component needed to produce a functional copy of itself, and assemble those components autonomously, without any human oversight, using only the resources available in that system. We cannot achieve this even on Earth, despite our vast industrial base and constant human supervision. We do not possess machines capable of reproducing themselves directly from raw materials without deep and constant human involvement. To imagine achieving such a feat in alien star systems, where the distribution of resources is unknown and where no human could intervene to diagnose faults or make repairs, stretches plausibility to an extreme. And even setting that aside, even if true self-replication were possible, an enormous bootstrapping problem immediately appears. A probe would have to arrive carrying sufficient machinery to begin mining, refining materials, and manufacturing complex components in an unfamiliar environment. All of that equipment has mass, and mass translates directly into higher launch costs and slower acceleration. On top of this, the probe would require a power source, perhaps large solar arrays or nuclear reactors, each adding further mass. It would also need highly advanced artificial intelligence to navigate between stars, to survey and interpret an entirely new planetary system, to identify usable resources, and to coordinate the entire manufacturing process autonomously. The more capable and autonomous you make such a probe, the heavier it becomes, and the harder it is to launch and accelerate to interstellar speeds. Then there is the question of reliability. A self-replicating probe would need to operate with extraordinary precision, because any mistake made during replication would be passed on to every subsequent generation. If a probe produces a flawed copy, and that copy produces further flawed copies, errors accumulate. You effectively introduce mutation and degradation. You end up with a form of evolution, but without natural selection acting to preserve functionality. Over time, the population of probes could drift away from the original design, lose critical capabilities, become dysfunctional, or evolve in directions never intended by their creators. This mirrors biological evolution in a striking way, and it raises a profound question. Would self-replicating machines remain under control, or would they eventually become something unpredictable and possibly uncontrollable? That leads directly to safety and ethical concerns. A genuinely self-replicating probe, once released, cannot be recalled, it cannot be stopped. If it malfunctions, or if it evolves in unexpected ways, or if it begins consuming resources aggressively or behaving destructively, there is no practical method to shut it down across the vastness of the galaxy. You would, in effect, have unleashed something with the potential to cause immense harm, while retaining no control over its future behavior. Would any responsible civilization willingly take such a risk? And then there is the question of purpose. What are these probes actually meant to do? If their role is exploration and data gathering, then they must communicate their findings back home. Yet communication across interstellar distances is slow and difficult. As probes move farther away, the delay in receiving their data stretches to thousands or even millions of years. By the time information arrives from distant stars, does it still have any value? Does anyone still exist who cares? If the probes are intended to prepare worlds for biological colonization, then they encounter all the same obstacles that biological colonization faces. There are no clearly suitable destinations and no compelling motivation to send colonists. If, instead, the probes are meant to establish machine civilizations around distant stars, then the problem has not been solved at all. You are no longer extending the original biological species. You are creating new forms of intelligence that may have little or nothing to do with the beings who launched the first probe. So self-replicating probes do not resolve the challenge of galactic colonization. They introduce their own severe technical, conceptual, and ethical difficulties. And even if they function exactly as intended, they fail to achieve the aims that biological colonization was supposed to fulfill. There is, however, another issue that I believe is absolutely central, yet it is rarely confronted directly in discussions of galactic colonization. That is the question of timescales and the continuity of civilizations. Even if we generously assume that every technical obstacle can be overcome, that energy is abundant, that generation ships are reliable, and that self-replicating probes operate flawlessly, a deeper question remains. Can any civilization sustain focus and commitment to a project spanning millions of years? I think the answer is almost certainly no, and the reasons are written plainly in our own history. Human civilization, in its recognizable form, with writing, agriculture, cities, and states, is about 5,000 years old. That is an eye blink compared to the timescales required for galactic colonization. And even within those 5,000 years, change has been relentless. Languages evolve, split, and disappear. Cultures transform beyond recognition. Political systems rise, dominate, and collapse. Technologies are invented, forgotten, and rediscovered. Religions spread, fracture, and fade. The Roman Empire once appeared eternal and unavoidable, yet it fell and now belongs entirely to the distant past. People living in medieval Europe could not have conceived of modern democracy, industrial technology, or the internet. Even today, we struggle to imagine what human civilization might look like 1,000 years from now, let alone 10,000, 100,000, or a million years into the future. When we speak of galactic colonization programs, lasting millions of years, involving thousands of colony ships launched over vast stretches of time, requiring uninterrupted investment, maintenance of infrastructure, and unwavering dedication to distant goals, we are assuming a level of civilizational stability that has never existed and almost certainly never will. What happens when priorities shift? When future generations decide that galactic colonization is a misuse of resources and that their attention should turn inward toward cultural, artistic, or spiritual development? What happens when economic systems change in ways that make long-term space exploration financially irrational? When political structures collapse and are replaced by new ones with entirely different values and ambitions? In such circumstances, any galactic colonization effort would almost certainly be abandoned long before it could succeed. Not because it is forbidden by physics, but because civilizations do not pursue the same objectives across such immense spans of time. Projects begin with enthusiasm, then gradually fade as generations pass and priorities evolve. And this offers yet another possible answer to the Fermi paradox. Perhaps many civilizations seriously contemplate galactic colonization. Some may even embark on grand, ambitious programs, only to abandon them partway through, because the timescales involved stretch far beyond what any civilization can realistically sustain. The galaxy remains untouched, not because spreading between the stars is beyond our technology, but because it lies beyond the long-term endurance of civilizations themselves. It demands a continuity of purpose and a depth of focus that no biological society has ever demonstrated it can preserve. There is, however, a closely related question that deserves careful thought, and it concerns the fate of any colonies that might actually be founded. Let us assume that, despite all the obstacles I have outlined, a fraction of interstellar missions do succeed. What then becomes of those settlements? Do they remain part of a wider network, cooperating, trading, sharing culture with their world of origin? Or do they slowly drift apart, becoming isolated, eventually severing all meaningful ties with their beginnings? I believe that isolation and divergence are unavoidable for interstellar colonies, and this alone dismantles the very notion of a galactic civilization. The reason is rooted firmly in physics. Communication between stars is constrained by the speed of light. A signal sent to Proxima Centauri, our nearest stellar neighbor, takes 4.24 years to arrive, and a reply requires another 4.24 years to return. That is an 8.5-year round trip for a single exchange. When we consider stars tens or hundreds of light years away, those delays extend to decades or centuries. For destinations thousands of light years distant, communication stretches across millennia. Under such conditions, real-time conversation simply cannot exist. Messages can be transmitted, but dialogue is impossible. There can be no negotiation, no coordination of shared activity, no sustained relationships in any meaningful sense. Communication becomes less like conversation and more like casting bottles into an ocean, hoping someone, somewhere, far in the future, might read them. Add to this the staggering cost of interstellar travel itself, and physical movement between colonies becomes effectively impossible. Once a settlement is established around another star, it is alone. There is no trade, no migration, no cultural exchange beyond the painfully slow trickle of messages carried at light speed. Isolation becomes absolute, and from isolation follows divergence. Colonies would develop independently, culturally, and perhaps biologically as well. Languages would drift, then fracture, and in time become mutually unintelligible. Cultures would branch in unpredictable directions, shaped by different environments and histories. Political systems and social structures would evolve separately, responding to local pressures rather than any shared authority. If biological adaptation occurs, whether through adjustment to alien environments or through genetic drift in small populations, then genetic divergence would follow too. Over thousands, or tens of thousands, of years, these colonies would no longer resemble branches of a single civilization. They would become entirely separate societies, sharing little more than a distant ancestral memory. They would not form a galactic civilization. They would be isolated communities that happen to trace their origins to the same place, yet possess no meaningful connection or interaction with one another. So even if the colonization of the galaxy were achievable, even if thousands of settlements were successfully founded, the outcome would not resemble a unified interstellar society. Instead, we would see thousands of isolated, diverging communities, permanently separated by distances too vast for communication or travel to preserve any sense of unity. This stands in stark contrast to the visions offered by science fiction, the Federation of Star Trek, the Galactic Republic of Star Wars. Vast societies bound together by rapid travel and instant communication across thousands of worlds. Such visions are compelling, but they are impossible because the laws of physics do not allow them. The speed of light is too slow, the distance is too immense, the resulting isolation too profound. What is far more plausible is a scattering of lonely colonies, each evolving along its own path, each gradually forgetting any shared origin, each potentially becoming a distinct species or civilization with no awareness of the others. And at that point, we must ask whether the galaxy has truly been colonized at all, or whether it has merely been seeded with isolated populations, each confronting its own hardships, and many likely fading into extinction when they fail to achieve long-term sustainability on hostile worlds. There is one final aspect of this problem that I think is essential to consider, and that is the role of evolutionary timescales and the transformation of species. The timescales required for galactic colonization, measured in millions of years, are the same timescales over which profound biological evolution occurs. Any species attempting such a project would not remain unchanged. It would evolve into something else. That evolution could render continued colonization either impossible or meaningless. To understand why, consider our own history. Humans diverged from our common ancestor with chimpanzees over a period of roughly 6 to 7 million years. That span of time was sufficient for a single lineage to split into two species with very different bodies, abilities, and behaviors. Any species spreading between the stars would likewise evolve in response to unfamiliar environments, new selection pressures, and the randomness of genetic drift. Human populations living on high-gravity worlds would be strongly selected for shorter, sturdier physiques, better suited to those conditions. Colonies exposed to intense radiation might evolve more efficient DNA repair mechanisms or suffer higher mutation rates with unpredictable consequences. Small, isolated populations would experience founder effects and genetic drift, altering gene frequencies by chance alone. Each colony would follow a different evolutionary path, shaped by its environment and by random events, steadily diverging from the others over deep time. Over immense stretches of time, the durations demanded to occupy meaningful regions of the galaxy extend across millions of years. Across such epochs, evolutionary change would not merely occur, it would compound, layer upon layer, until the original colonists and their distant offshoots were no longer the same kind of being at all. Entirely new species would emerge, perhaps incapable of interbreeding with one another, and certainly unable to do so with the population that once set out from the homeworld. And this leads us to the pivotal question: if a colonizing species fragments into numerous species or subspecies during the long process of spreading through the galaxy, can that still be described as a single colonization endeavor? Does it still fulfill the intention with which it began? Imagine that humanity launched a program of galactic expansion, and 1 million years later, the galaxy contained thousands of species descended from humans, none of them recognizably human in their bodies, their minds, or their cultures. Would we honestly call that a success? Or would it instead represent such a profound biological and cultural transformation that the original objective had effectively dissolved? I would argue for the latter. The beings inhabiting the galaxy 1 million years into such a program would not be the species that initiated it. They would be descendants, yes, but shaped so thoroughly by time and evolution that they would share little, if anything, with their ancestors. And there is no reason to assume that these transformed descendants would retain the same interest in continuing the expansion. Their values could be different, their priorities altered, their worldview molded by unique evolutionary paths and unfamiliar environments. The colonization effort might simply fade away, not through catastrophe, but through indifference. No one would care to continue it, because the beings who exist at that time would not share the motivations of their long extinct predecessors. In this way, evolutionary time alone erodes the internal logic of any long-term colonization plan. The species that begins the journey is not the species that would ever finish it, assuming it could be finished at all. And this stands as yet another reason why galactic colonization cannot succeed for biological life. The immense time spans involved guarantee that the colonizing species will change into something else long before completion, and that something else may see no reason to carry on. Now let me draw together all the strands of this discussion into a single, coherent picture of why galactic colonization is impossible for any biological species. The obstacles are numerous, mutually reinforcing, and deeply rooted in the nature of reality itself. The distances involved are simply too great. Even at highly optimistic velocities, traversing the galaxy requires millions of years. The energy demands are staggering. Even civilizations far more advanced than ours could not reasonably afford to construct, launch, and sustain thousands of colony vessels indefinitely. The destinations themselves pose another problem. Truly habitable worlds are extraordinarily rare, perhaps absent altogether within any reachable range. The technical challenges are overwhelming. Generation ships cannot realistically preserve full functionality across thousands of generations. Complete self-sufficiency remains unattainable. Even self-replicating probes encounter formidable practical limitations. The biological challenges are equally severe. Maintaining healthy populations over vast spans of time, preventing genetic deterioration, and adapting safely to alien environments present nearly insurmountable difficulties. The psychological and social challenges are just as daunting. Sustaining morale, cooperation, and social stability in isolated communities for thousands of years while avoiding collapse or abandonment of purpose stretches credibility beyond its limits. Then, there is the problem of motivation. There is no compelling reason for a species to commit enormous resources over millions of years to a project that yields no immediate or practical return. Civilizational time scales themselves pose an insuperable barrier. No civilization maintains coherence, continuity, and shared intent across the millions of years demanded by galactic expansion. Communication delays and cultural drift ensure that colonies would become isolated, diverging not only from their point of origin, but from one another, evolving into separate societies rather than members of a single galactic civilization. And finally, evolutionary time guarantees transformation. Over millions of years, species change into new species, dissolving any long-term unity of purpose and rendering sustained colonization incoherent. Each of these barriers on its own would make galactic colonization extraordinarily difficult. Taken together, they render it effectively impossible. And because these limits arise from fundamental principles of physics, biology, psychology, and sociology, rather than from shortcomings of present-day technology, they apply universally to all biological species anywhere in the galaxy, not merely to us. An extraterrestrial species might surpass humanity in intelligence, possess more advanced tools, enjoy longer lifespans, or display greater patience and cooperation, but it cannot alter the speed of light. It cannot ignore the conservation of energy. It cannot evolve bodies that require no resources or environments. It cannot sustain a single civilizational focus across millions of years. It cannot halt evolutionary divergence. The same barriers that confine us would constrain them as well. And this, I believe, resolves the Fermi paradox entirely. We see no evidence of galaxy-spanning civilizations because such civilizations do not exist and cannot exist. We do not observe colossal structures or vast feats of astroengineering because the motivations behind such endeavors never outweigh their immense costs. We see no signs of widespread colonization because colonization itself is impossible. The galaxy may be filled with isolated oases, planetary systems where life can arise, and civilizations may briefly flourish. But those oases remain forever separated by deserts of space so vast, and by demands of time and energy so extreme that meaningful connection can never be achieved. And it is from this perspective that we arrive at a complete understanding of why galactic colonization lies forever beyond the reach of biological species. Not merely challenging, but truly impossible, because of a convergence of constraints rooted in fundamental physics, in biology, in psychology, and in the structure of societies themselves. What I want to consider now is what this reality implies, what it means to exist within a galaxy where intelligent species are permanently confined to their home systems, forever divided from one another by distances that simply cannot be crossed. I believe that grasping the impossibility of galactic colonization reshapes how we ought to think about our place in the universe, about the search for extraterrestrial intelligence, about our long-term future, and about the responsibilities that come with being a technological species. To begin, let us consider what this tells us about how life and intelligence are distributed across the galaxy. The fact that colonizing the galaxy is impossible tells us nothing definitive about whether life itself is abundant or exceedingly rare. Life could emerge readily wherever the right conditions exist, or it could be an astonishingly rare phenomenon. Intelligence might follow naturally from complex life, or it might be a 1 in a billion accident. These questions remain unresolved and are the focus of active scientific research. What the impossibility of galactic colonization does tell us, however, is that no matter how frequent or infrequent intelligence may be, intelligent species are isolated. Each one comes into being independently, on its own world. Each develops alone, without contact or influence from others. Each confronts its own problems, makes its own decisions, thrives or collapses on its own terms. There is no galactic civilization, no federation of cooperating intelligences, no exchange of knowledge, culture, or resources across the stars. Every intelligent species exists in solitude, separated from all others by distances and timescales that cannot be overcome. As a result, the galaxy is not settled, not populated by the descendants of ancient civilizations, not crossed by starships or linked by vast communication networks. Instead, it remains untamed, a place filled with isolated enclaves of intelligence that appear, endure for a while, and ultimately disappear without ever meaningfully interacting with one another. Every planetary system that hosts intelligent life is like an island in an immense cosmic ocean, self-contained, isolated, cut off from all other islands by distances far too great to traverse. At first glance, this may seem like an unbearably lonely vision, and in some sense it is, but it is crucial to distinguish between being alone and feeling lonely. Being alone is simply a statement of fact. There is no one else nearby, no exchange with alien intelligences. Loneliness, on the other hand, is an emotional condition, the feeling that something desired is missing, the yearning for a connection that cannot be found. And I do not think that our solitude in the galaxy must inevitably lead to loneliness, because loneliness depends on the expectation of a connection that does not exist. If we understand and accept that contact with alien intelligence is impossible, that our isolation arises from fundamental features of the universe, rather than chance or misfortune, then we can release those expectations. We can turn our attention instead to the life and intelligence that are accessible to us, to one another, to Earth's biosphere, and to the extraordinary richness of human culture and experience. Let me say this another way. For many decades, we have searched for evidence of extraterrestrial intelligence through SETI programs, by listening for radio transmissions, by looking for technological signatures and massive artificial structures, by studying exoplanets for signs of biology. And these efforts matter. They have advanced our technology and deepened our understanding of the universe even in the absence of detection. Yet they are also driven by a hope, perhaps an assumption, that we might not be alone, that somewhere out there exist others with whom we could communicate, from whom we might learn, whom we might one day encounter. I think the impossibility of galactic colonization tells us that these expectations need to be reconsidered. We should acknowledge that even if intelligent species are widespread throughout the galaxy, we will never detect most of them. We will never exchange meaningful messages with them. We will never gain the cosmic perspective that direct contact might offer. We are permanently isolated, not because other intelligences do not exist, but because the architecture of the universe prevents contact. This does not mean that we should abandon SETI altogether. There is still value in searching, in testing our assumptions, in verifying whether our understanding is correct. And there remains a very small possibility, though I believe it is vanishingly slight, that we could detect a radio signal or another technological signature from a relatively nearby civilization, perhaps within a few dozen or a few hundred light years. If such a detection were made, it would be scientifically profound, even if true communication proved impossible because of the immense time delays involved. It would tell us that intelligence arises elsewhere, that we are not unique, that technological civilizations do, at least occasionally, emerge within our galaxy. That kind of knowledge would have value even if communication flowed only one way, but we have to be honest with ourselves about likelihoods. We should weigh probabilities carefully and avoid pouring vast resources into searches that, realistically, have a very small chance of success. A restrained program for the search for extraterrestrial intelligence, one that makes use of telescopes and computing power we already possess, is sensible. A dramatic escalation, one that consumes large portions of our scientific funding, is not justified when detection is so improbable and when the practical benefits would remain limited even in the unlikely event of success. Now I want to turn to what the impossibility of colonizing the galaxy tells us about ourselves, about the future of humanity, and our position in the universe. Many visions of our destiny assume that one day we will expand outward, that Earth is merely the first step, and that our true future lies scattered among the stars. But if that assumption is wrong, if spreading across the galaxy simply cannot happen, then we are forced to rethink humanity's long-term path in a profound way. The familiar image of humans establishing settlements on thousands of distant worlds, transforming into a fully spacefaring civilization, is not achievable. It will not come to pass. The laws of physics stand in the way. Our biology offers no support for it. The economics collapse under scrutiny. The incentives are weak. The timescales stretch far beyond anything practical. We will not become a species that inhabits the galaxy. We will remain bound to Earth, or at most to our local solar system, for the entirety of our existence. For many, this realization feels dispiriting, even bleak. The idea of humanity spreading across the stars is intoxicating. It speaks of infinite opportunity, of unbounded growth, of our species attaining a kind of cosmic importance, of descendants living and thriving on innumerable worlds. Letting go of that dream can feel like accepting a smaller future, like conceding loss, like abandoning something grand and inspiring. But I want to offer another way of seeing it. Accepting that our home is Earth and its immediate surroundings is not a narrowing of possibility. It brings clarity. It directs our attention to what truly matters, to what we can actually accomplish, to the task of building a civilization that endures and flourishes here, rather than chasing visions of expansion that were never realistic to begin with. Earth and the wider solar system already provide an immense canvas for meaningful human futures. Earth itself is remarkable. It is the only world we know that hosts life, the sole place in the universe where the particular evolutionary story that led to us has unfolded. It contains extraordinary biological richness, millions of species and ecosystems that range from tropical rainforests to coral reefs to Arctic tundra. It is a planet of immense beauty, with mountains and oceans, deserts and forests. It holds thousands of years of human history and culture, languages, art, architecture, traditions, and accumulated knowledge. Most importantly, it is the only environment in which human beings can live without technological assistance, where we can breathe the atmosphere, drink the water, and grow food as part of the natural world. These qualities are precious and cannot be replaced. There is nowhere else in the galaxy like Earth. There is nowhere else where we could live with the same depth and fullness that we experience here. Recognizing how unique Earth is and accepting that it is our only viable home should deepen our appreciation rather than diminish it. It should strengthen our resolve to protect it, to care for it, to ensure that it remains a place where future generations can thrive. Beyond Earth, our solar system still offers real opportunities. We may establish research stations on the Moon or on Mars, small outposts dedicated to scientific discovery. We might construct habitats in orbit, though these would not be cities in any meaningful sense, but rather specialized environments for research or limited habitation. We could extract resources from asteroids to support industry on Earth and activities in orbit. None of these ambitions require journeys between the stars or permanent settlement on hostile planets. They are all achievable within our solar system, using technologies we can reasonably foresee and resources that are plausibly available. Our future in space is not empty or insignificant. It is simply local, focused on our immediate cosmic neighborhood, grounded in purposes that make sense rather than in fantasies of endless expansion. Within these boundaries, the potential for human achievement remains vast. We can build a sustainable civilization on Earth that endures for thousands or millions of years. We can create art, culture, and knowledge of extraordinary depth. We can explore the universe through telescopes, robotic explorers, and theoretical insight. We can develop technologies that enhance human well-being, reduce suffering, and open new realms of experience and creativity. We can inhabit Earth in ways that protect ecosystems instead of destroying them, that work with nature rather than against it. All of this lies within our reach. All of it is valuable. None of it depends on colonizing the galaxy. In that sense, accepting our confinement to Earth is not a loss of freedom, but a gain. It releases us from impossible aspirations and brings our focus back to goals that are achievable and genuinely important. And this leads me to something closely connected, something I believe is crucial, yet often neglected: the question of what our apparent isolation means for meaning and significance in the universe. Many people draw a sense of purpose from imagining humanity as part of a vast cosmic community, as one intelligence among many, participating in some grand galactic narrative. If we are alone, if there is no wider community and no story beyond our own local one, does that strip our existence of meaning? I do not believe it does, and I want to explain why. Meaning does not arise from some grand cosmic importance or from belonging to a vast galactic story. It emerges from consciousness itself, from the fact that we are aware, that we feel, that we reflect, that we choose. Meaning is found in the experiences we live through, in the values we hold, and in the decisions we make. A life becomes meaningful when it is filled with experiences that are worth living, relationships that are worth caring for, projects that deserve our effort, and moments of beauty that invite our attention. None of this relies on the existence of extraterrestrial life, nor on humanity being part of a wider galactic civilization. The bonds you share with other people matter because you care about them and they care about you, not because those bonds echo across the cosmos. Art, music, and literature matter because they shape our inner lives and express something deep about what it means to be human, not because some distant intelligence might one day observe them. Scientific understanding is valuable because it satisfies our curiosity and allows us to engage with reality more clearly and more effectively. Not because it feeds into a universal archive of galactic knowledge. Our apparent isolation does not strip life of meaning. If anything, it sharpens our understanding of where meaning truly comes from. It does not come from outside us or from some imposed cosmic purpose, but from our own awareness, our capacity to value, and our freedom to choose. We generate meaning simply by living, by caring, by dedicating ourselves to people, ideas, and goals that matter to us. That, in itself, is enough. It is all the meaning we require. In fact, accepting our isolation can deepen that meaning because it reminds us how precious what we have really is. If Earth is the only habitable world we will ever know, if human civilization remains alone and never becomes part of a wider galactic community, then everything we create here, everything we achieve and preserve, is singular and irreplaceable. We are not merely one civilization among millions. We are the only civilization we know of, and perhaps one of very few in the galaxy, and certainly the only one with which we will ever have meaningful contact. That does not make our achievements smaller. It makes them more significant, because they are not duplicated elsewhere, because they exist only here, and because they will vanish forever if we fail to protect them. In this sense, meaning grows when we accept our isolation rather than shrinking away. We matter more precisely because we are all we have. Our choices carry greater weight because there is no parallel experiment unfolding elsewhere that we can rely on or learn from. Our responsibility to Earth and to future generations is therefore greater because there is no backup, no alternative refuge, no rescue arriving from distant civilizations, and no escape to other worlds. There is, however, a question that many people find especially challenging when they confront the idea that galactic colonization may be impossible. It is the question of the very long term, of what happens billions of years from now, when the Sun reaches the end of its life, and Earth can no longer support life. If we cannot travel to other star systems, if we are confined to our solar system indefinitely, does that mean humanity is ultimately doomed? Does it mean that our species will inevitably disappear when the Sun dies, regardless of everything we have accomplished? The honest answer is yes. The Sun will eventually exhaust its fuel in about 5 billion years. As it does so, it will swell into a red giant and will almost certainly render Earth uninhabitable long before that final stage, very likely engulfing the orbit of our planet. If leaving the solar system is impossible, then any civilization rooted on Earth or within the solar system will come to an end when the sun dies. In that narrow sense, it is true that our fate is sealed. But this needs to be placed in proper perspective. 5 billion years is an almost unimaginable span of time. It is longer than Earth itself has existed, since Earth formed around 4.5 billion years ago. It is more than 1,000 times longer than complex multicellular life has been present on this planet. It is millions of times longer than the entire history of human civilization. Everything we think of as human history, writing, agriculture, cities, nations, science, technology, and art, has unfolded within just a few thousand years, roughly 1/1,000,000th of the time that remains before the sun dies. So while it is true that there is an ultimate end far in the future, that end lies so far beyond any timescale we can realistically plan for or emotionally grasp that it has no bearing on how we should live today or what we should value. By the time the sun reaches the end of its life, if humanity or its descendants still exist, they will have transformed into something utterly different from us. The beings that exist 5 billion years from now would be as distant from modern humans as we are from bacteria. They may not even be biological. They could be forms of machine intelligence, uploaded consciousness, or entities beyond anything we can currently imagine. Whatever their nature, they will confront their own circumstances and make their own decisions. It is neither our responsibility nor within our power to solve problems that lie billions of years ahead for beings who will not be us in any meaningful sense. Our responsibility lies with our own generation and with those that immediately follow on timescales of hundreds or thousands of years, where our actions genuinely shape outcomes and where our choices truly matter. On those timescales, Earth remains a perfectly viable home. Our focus should be on building a sustainable and flourishing civilization here, rather than worrying about the death of the sun billions of years in the future. For that reason, the eventual fate of our solar system does not diminish the value of what we build on Earth today, nor does it make galactic colonization a necessary form of salvation. The ultimate catastrophe lies so far ahead in time that it has no bearing on the choices we make today, and the beings who may one day confront it will not be us, nor will they be grateful that we presumed to decide on their behalf billions of years ago. With that in mind, let me turn to one last consequence of the fact that spreading across the galaxy is, in practice, impossible. It concerns how we ought to think about our bond with Earth and with the other forms of life that share it. Because once we truly grasp that we are bound to this planet, that it is our only home and will remain so, it places moral demands upon us that are deeper and more immediate than we might otherwise acknowledge. If humanity could settle other worlds, if Earth were merely one option among many places we might inhabit, then harming this planet would be a tragedy, but not necessarily an existential one. There would be alternatives, other destinations to turn to should Earth cease to support us. But if Earth is the sole place where human civilization can exist, if there are no backups waiting elsewhere, then to destroy Earth is to erase the only stage on which our story can unfold. In that case, our duty to protect this planet is total. We simply cannot allow climate change or nuclear conflict or the slow erosion of our environment to render Earth uninhabitable because there is nowhere else to go. This is it. We are confined here, and if we ruin our home, we bring about our own end. From this follows, I think, a profound moral responsibility to safeguard Earth's capacity to sustain life, to care for the biosphere, and to prevent changes so severe that the planet can no longer support human civilization or the countless other species that depend upon it. This responsibility does not stop with humanity, important though our welfare is. It extends to the millions of other species with whom we share this world, each with as much claim to existence as we have, each relying on the same fragile web of life. If Earth is the only place we know in the universe where life has arisen, then its biosphere possesses an extraordinary cosmic value. This planet is not merely our home, it is the only known example of life anywhere at all. Every species is singular, every ecosystem cannot be replaced. Every extinction is final, the disappearance of something that will never exist again, anywhere. And we, uniquely, are the species with the power either to preserve this living system or to dismantle it on a planetary scale. With that power comes an immense responsibility. We can choose to act as careful custodians of Earth, protecting its richness, its beauty, and its capacity to function for future generations of humans and for other life forms. Or we can choose a path of destruction, exploitation, and short-sightedness, degrading the very systems that sustain us until the planet becomes uninhabitable or, at the very least, far poorer and less diverse than it once was. The realization that we cannot spread across the galaxy makes this choice starker and more urgent. There is no escape route. We cannot abandon Earth when its problems become inconvenient. We cannot treat it as something disposable. Either we make it work here, or we fail altogether. And that fact, I think, brings the challenges before us into sharp focus. Climate change, the loss of biodiversity, pollution, the depletion of resources. These are the problems that demand our attention, and they demand solutions. Not fantasies of escape, not hopes that some future technological miracle will allow us to leave Earth behind, but serious commitment to preserving the world we have. Now, I want to draw these threads together and turn to what I see as the central message running through this entire discussion. And it is this: the universe is not arranged in a way that allows beings like us to traverse it freely. The distances are immense when set against the speeds we can realistically achieve. The energy demands are overwhelming when compared with the resources available to any civilization. The timescales stretch far beyond biological lifetimes and the continuity of societies. The environments between the stars are fundamentally hostile to life as we know it. The incentives are weak when weighed against the enormous costs and difficulties involved. Every obstacle I have described, and there are many that reinforce one another, arises from the basic laws of physics, the realities of biology, and the nature of societies. These are not shortcomings of present-day technology or temporary features of human culture. They are not challenges that will vanish with future breakthroughs or with wiser civilizations. They are enduring aspects of how the universe operates, limits that apply to any biological species, anywhere in the galaxy. The speed of light does not change. The conservation of energy holds everywhere. Living organisms, wherever they arise, require resources and environments compatible with how they evolved. Civilizations everywhere struggle with coordination and survival across long spans of time. Species everywhere change on scales of millions of years. These are not uniquely human difficulties. They are universal constraints on what complex, evolved beings can achieve. And those constraints imply that intelligent species, wherever they emerge, remain isolated. They grow and develop on their home worlds. They may explore nearby space, send machines to neighboring stars, perhaps even exchange signals with other civilizations if such neighbors exist and can be detected. But they do not settle the galaxy. They do not spread across thousands of star systems. They do not construct vast galactic civilizations linking millions of worlds together. The galaxy is not, and in truth cannot be, colonized by biological life. It remains vast and untamed, disconnected, a place of scattered islands where life may emerge and intelligence may briefly bloom, yet those islands are destined to remain eternally separated. This, I believe, is the real resolution of the Fermi paradox. We see no sign of galactic civilizations, not because intelligent beings are necessarily uncommon, although they may be, and not because civilizations inevitably destroy themselves, although that too may happen, but because the very idea of a galactic civilization is fundamentally unworkable. The obstacles to traversing the galaxy are so deep, so rooted in the laws of physics and the limits of biology, that no species can overcome them, no matter how advanced, ingenious, or persistent it might become. The galaxy is filled with silence, not because there are no voices, but because those voices are unimaginably distant from one another, too far apart to be heard, too isolated to exchange signals, too constrained by nature itself to bridge the gulf between them. We are one such voice, alone in our small region of the Milky Way, asking whether others exist, yet unable to reach them, unable to listen to them, unable even to know with certainty that they are there at all. This is our cosmic condition, isolated, alone, confined to our local neighborhood of space by barriers that cannot be crossed. And I think that truly accepting this, really absorbing it rather than clinging to hopes of contact or indulging in dreams of galactic expansion, is essential if we are to think clearly about who we are and what we owe to one another. We are not going to encounter aliens. We are not going to become members of some vast interstellar society. We are not going to spread across the stars. We will remain here on Earth, and perhaps within our solar system, for as long as our civilization endures. And that is not a disaster. It is not a defeat. It is simply the consequence of being a biological species in a universe built the way this one is. Our responsibility is not to fight against that reality. We cannot. Our responsibility is to accept it, and within those limits, to create the best civilization we possibly can, to cultivate meaning, beauty, and understanding here, on this single world that is ours, to protect Earth and its living systems for as long as we are able, to lessen suffering and to expand the possibilities for flourishing, for humans and for the other forms of life that share this planet with us, to value what we have instead of yearning for what lies forever beyond our reach. The galaxy will remain unclaimed and largely unexplored, wild and quiet, save for isolated sparks of intelligence that appear, persist for a time, and then fade away without ever truly touching one another. That is the character of the universe we live in, and it is enough. Earth is enough. Our solar system is enough. Human civilization, here and now, is enough. We do not need the galaxy. We need only to care properly for the world we already possess. We are cosmically isolated, and we will remain so forever. And when that isolation is understood and embraced, it sharpens our focus on what genuinely matters. Not expansion, not conquest, not some imagined galactic destiny, but the task of building good lives here, now, on the only world that can ever truly be our home. The galaxy cannot be traversed. We are tied to Earth, and Earth is where we belong, where we can thrive, where our future unfolds, not among distant stars, but here, on this remarkable planet that gave rise to us and that will sustain us if we are wise enough to protect it. This is our place, this is our home, this is where we belong, and it is enough, more than enough. It is everything.